Welcome to the first week of the Advanced Water Workshop here at Rebelway. I wanted to take this opportunity to say hi to all of you and to really introduce myself and this workshop to all of you so you know what you're getting yourself into now here. So I've been a water FXTD for about 10 years now. I've been most of that time at important looking pirates in Sweden, focusing a lot at developing workflows and methods to really achieve a high volume of high-end, outstanding FX work. Over the years, I've been recognized and nominated for my work multiple times, and I'm quite proud of the fact that we've always achieved that with very small teams of very talented, very driven artists. That goes from the animators up to the compers and the lighters who really make all of my stuff look fantastic, right? Visual effects is 100% a team sport, and all we're doing with effects and with water is telling a small part of the story. Now, I've always believed that telling that part of the story in a very efficient and organized manner that allows the other artists and supervisors to see things fast, to see things early and reliably, to be able to really talk about what's going on in a shot and be able to feedback and art direct motion with it being possible to do so is invaluable for everybody else in the team and quite frankly for anybody who you work with. So I'm going to teach you guys not how everything is solved. I'm not going to teach you if you press those 5 buttons in this way things will work. I'm not going to teach you, well, type in these values into the whitewater solver and you'll get beautiful results. What I will teach you is how to break down complicated simulation shots, how to look at them in a different way, how to build small, scalable systems that can be tested individually and then linked together like a big Lego model, right? That's what this course is. It's a way of looking at a Star Destroyer from Star Wars and going, hey, this is not 5 million complex pieces, it's actually just 5 billion small bricks that interlock to each other, and together they build this big system, right? We're going to look at different solutions and different methods to approach very specific as well as very broad issues, right? We're going to look at how can I circumvent shortcomings of the default Houdini tools, and how can I look at them in a different way and take bits and bobs of it that are very useful in certain cases and build them into my systems. We're going to look at how do I test my systems small while knowing that they're scalable, right? This course is hopefully going to bring you to a place where you can jump into any production and operate at a high level. I want you to join any show and be that kick-ass artist who the supervisor can lean on with his feedback, with his art direction, and really push the show to the next level. It's not going to be, this is how I can do some fancy little shots at home. It's really going to be, how do I approach things at scale? How do I look at problem solving at scale? How do I build systems that allow me to kick off 50 sims on a Friday afternoon, go home and enjoy the weekend, out having to check the farm, out having to make sure that everything worked because you know it will. It's about reliability, predictability, and scalability. I'm hoping to be able to teach all of you how to work in such a manner and how to be that brick and how to be that foundation in any show you work on. I want you guys to be badass. I want you guys to be the best you can be after this course. In this video, we will be taking a look at the basics of flip simulation. In order for us to get a good understanding of the resolution as well as the domain settings of a simulation, we will be making a small example scene of a flip tank containing a rotating donut, which we will then cache out to disk. So let's get started. First, the easiest way for us to make a flip tank and really any flip container within Houdini is to use the shelf tools. Now, by default, you will be coming in on the Lights and Camera tab, but you want to head over to the Particles Fluid tab. Here you will find the Flip Tank option, and you just press that and hit Enter, and the option for it comes up. Now, this creates a bunch of nodes for us within Houdini. right? We have our simulation network and also a bunch of geometry nodes. Now the flip tank initial is basically creating the source for this water simulation. Then flip tank fluid imports all of our simulations, and fluid interior is used for render purposes. So right now we don't need that, and I'm just going to delete it. Cool. So let's look at the source first and see how all of this is defined. We go into the flip tank initial. We will see that there's an object merge in case you have collisions. Right now we don't have any collisions, so we can actually just delete this. Now the ocean source, here called wave tank, is really the object that defines and sources and builds all of these tank solutions within Houdini. Later on, when we will be looking at guided simulations and that kind of stuff, they also use the same node. So here this node defines the domain of our simulation. So if we would make this box a lot bigger, our simulation gets a lot bigger as well, right? So the settings for the domain, all of this is driven from our ocean source. Now resolution, oversampling, all of these things, these are all linked to our simulation network, right? So really the wave tank is setting up our boundary box and make sure that we fill it with particles where we need particles, and make sure that the initial fields and everything is being exported to the simulation the way Houdini likes it. Okay. One additional thing that can be done here for now is changing the wave level, the water level, if you want to. By default, 0 is pretty much the correct value to choose. But if you would ever run into the situation where you have to change the water level and, for example, simulate a little puddle on a 2-meter high pedestal, you could change it here, right? So this node sets up our source and gives us the confinements for our simulation. Now down here, we just split out the particles and the surface field if we do narrowband, and these are just hooks that are set up for Houdini to pick them up within the simulation network. And normally and usually you should just not touch those. Houdini needs them, and that's all you need to care about. All the settings you need are on the ocean source. All right, let's head into the simulation network and see what's going on there. So the basic flip simulation network is actually really simple, and that is for very basic simulation. All you need to make a flip simulation work is a flip object and a flip solver. Everything else is just nice things to make the flip look cooler. But this is an effective and working flip simulation, as we can see when I hit play, right? We have our water, we get some moving things down here, but we have a full-on water simulation. So let's take a closer look at the flip object, which actually contains the simulation. If we look at the geometry spreadsheet, we will see that under the flip tank, which is just a flip object called flip tank, we have a bunch of different things. We have our geometry container, which contains all our points, all their attributes, all of that good stuff right here. And then we also have a bunch of volumes. We have our collision volumes, collision velocity volumes, our surface and velocity volumes, our viscosity volumes. All of these guys live on this flip object. Now, here it is very important to establish a base fundamental knowledge of the flip solver. And that is that a flip solver is a volume solver, right? So it does not solve like a pop solver. It does not solve anything on the points. The points are there to carry a bunch of attributes, to carry a bunch of data, and to visualize and to be high resolution, to be a good representation of what the solver does, right? We need these particles to have detail in the mesh and to have a lot of information to output. But what the solver does is it takes all of these points and then projects them into the volumes, right? For example, all of these velocity attributes, they get projected into the velocity volume. Then all of these fields get solved, they get vectored, they get calculated, determines where the water should go. And then after that, it updates the velocity field, then it vects your particles, and reprojects all of those attributes back onto the points, right? So it's very important to understand that flip visualizes points for you. We use the points for meshing, we use the points for everything down the line, but internally a flip solver simply works on volumes, right? So it's always important to make sure that your volumes are there and your volumes are stable. Now, on the flip object itself, we can see a bunch of settings here for resolutions, physical settings, initial data, all of them, right? So let's go over the basics of resolution settings on flip. Now, compared to the standard, for example, pyro solver with a smoke object, which has 1 resolution setting, Houdini comes in with 3 flips or flip settings, right? Which is quite a bit more and makes it a little bit more complicated. But in the end of the day, it is very straightforward. And that is, you have particle separation, which is the resolution of the simulation, right? That is the main scale. That's the main thing you want to change to affect the rest of your sim. So if we would go 0.2 here, you would see a lot fewer points. Everything is lower res, right? So let's put this back to 0.075. Right underneath that, we have particle radius scale. So the particle radius scale makes the p scale of these particles bigger, makes their influence bigger. So if you have a very high volume simulation where you want very little small detail, you can increase the radius here or decrease it respectively. Honestly, I find simulations go quite haywire and become very unpredictable as soon as you start messing with this value. So I normally just leave this by default to 1.2, and the times I touch this value in my career, I can literally count on my fingers, and none of the times it worked out. So let's just leave this as is. Now, grid scale is a very, very interesting value. Grid scale comes back to the idea that the solve of the flip is done on volumes, right? Which means we need to carry all of those grids. We need to have all of that data here. Now, grid scale defines the resolution of all of these volumes. We set this to 0.1 for ease, and we look at the division size of, for example, the velocity field. We see that it's 0.2, which is your particle separation multiplied by your grid scale. Set this to 5, it'll be 0.5. Now, the reason this is important is because Houdini solves at a lower resolution than what you're actually simulating at. Now, that is a very, very good thing in most cases, because you don't need as many voxels as you need particles in order to describe a really cool motion, right? You can have a really high resolution splash, but you don't have to have these super crazy high resolution volumes. And especially looking at this, we can see there's quite a few of these volumes. So if all of these are super high res, your simulation is going to take ages, right? So Houdini by default said, hey, let's just simulate our volumes at double the resolution than what the user wants the final resolution to be. And because we project everything back to points, we can just have more points than voxels, filling in these gaps, giving that additional breakup, giving that additional detail, making things look like they're very high resolution with less costs up front. Right underneath the grid scale, we find the part collision separation. Now, collision separation is a fun one. It is there mainly because often if you deal with very thin collisions, the collision field is just not high resolution enough to capture that. And you get these holes and your water flows through your holes and you're wondering what's going on. And you're like, oh, I need to increase my resolution and I need to decrease my grid scale and all of that. And in reality, all your volumes are working. It's just your collisions are not precise enough to meet. So what side effects introduced is this checkbox. And this checkbox, compared to everything else, is actually not a multiplier, right? So this is not a multiplier of your particle separations. It just hard sets the resolution of everything in your collision field to whatever you type in here, right? So if you need to get really, really precise collisions, you can just oversample the collision field and leave everything else at a grid scale of 2, and you will be just fine, right? So instead of oversampling all your fields, check if maybe your collisions are the only thing that need a little bit of boost in the resolution. Now, right underneath that is something that's a bit strange and a bit different from all the other solvers within Houdini, and that is we have our closed boundary options. Now, again, if we bring up a smoke object, for example, we see those exact same settings here. And they work the same way, right? If I don't close my boundaries, the water will just go out to the edges and just disappear when it leaves my container. As soon as I close those boundaries, everything is good, right? And my water can't escape this box. It collides with all of these surfaces. And if we, for example, just for fun, turn off set negative, then the water runs out of this area and nowhere else, right? And we're slowly starting to leak water. Now, what is strange and what is different is that, for example, the smoke object, all the boundary layer settings, like where the box ends, is right on the object. So the object defines how big the area of the simulation is. With flip simulations, that is not the case, right? With flip simulations, to actually find out what these values are and change them, we need to go to the flip solver, over to volume motion, and here on the volume limits, we now see that we have the box size and box center options that we are used to. Now, in our case, because we used the tools that come with Houdini by using the flip tank option, these are automatically linked to our initial wave tank, right? So that goes back to our geometry node here, really controlling the size of our simulation and all of that living here, right? Now, as you can see here, the resolution that this guy operates at, that's coming from the dot network. So it's just the size that's being driven, which then feeds in here. All right, so if you're looking for boundary layers, especially if you make a new flip solver and you're like on a new flip object, right, and you're building stuff from scratch, don't go looking for how big your box is, anything on the object. Remember, flip solver, volume motion, volume limits. Cool. So the other settings on the flip object are the initial data settings. So the initial data settings are really only needed if you're wanting to start out with an initial field, just like everywhere else. But there is a few input type options that Houdini comes with. So by default, it will use narrowband, which is a very efficient way of simulating ocean tanks, or well, just tanks filled with water. If I change the background to dark, see stuff here, we can see that the volume, our simulation container, right, is empty at the bottom. Now the reason for that is narrowband simulations. Again, because the solver is all volume based, but we're visualizing and we're operating on particles. Side Effects came up with a really nice solution of just removing all the particles that are not close to the surface of our simulation. Because all these particles are just used for detail, they're used for extra meshing resolution and to carry very precise attributes later down the line, we don't need them down here. All of these particles down here, they are just wasted. They slow down our computing, right? So with narrowband, we are removing those. If I switch this over to a particle field, then we see that this whole container now is full of particles, and we simulate all of them, and all of them get advected, and all of them get sampled, and we're adding a lot of overhead to our simulation, right? So unless it's absolutely impossible, simulate your things with narrowband, it is just more efficient and it's better for you to run. And by default, it needs the initial particles as well as a surface layer just for Houdini to have that initialed so that it can run the narrowband. If I would remove this, it would still work, but Houdini really prefers having that field initialized. because now everything drops down, right? That is a requirement that only narrowband has. Particle volume, particle field, for example, does not need the surface layer, right? Switch that back to narrowband. Then on top of that, we have the guide options that are the usual guide options with, you know, all your settings per visualizer here. The only thing here that is really big to keep in mind and to change is if you go over to particles, visualization, by default this is spheres. And spheres is a horrendous way of looking at simulations. It's these big spheres, specular, and they slow down your GPU, they slow down everything, especially once you get to higher resolutions in your simulation. I literally had cases where my whole computer crashed, even though the simulation didn't run yet, just trying to draw the first frame. So visualization, change this to particles, and you can even save this just as the defaults as this is now. That is something very important to keep. Now, like every other object in simulations, this flip object also carries all the physical properties. You have your standards of bouncing forward, friction, temperature. Density is a new one. By default, it's 1000, which is the density of water. We will be going into this a little bit more in a later video this week, and in quite some detail in the waterfall tutorial later in this workshop. And viscosity can also be found here. We will be covering viscosity and its different options later in this week as well. Right? And then we have collision objects here, which is just changing some of the settings here. Again, I've never really used this. I would not touch it, I would not change it unless you really have to, right? Yeah, just leave this stuff here. Cool, so let's take a little look at the flip solver and just making sure that we get some basics covered here. And the one thing I want to talk about in this video is just narrowband, because this comes with the sourcing. So we're selecting narrowband as our initial here. And then we also need to go and take a look at the narrowband settings on the solver. Now, these are very bare bone and very simple. The important part here is bandwidth. And bandwidth is just how many voxels of particles should we keep around the surface level, right? So if you increase this, you get more particles. You decrease it, you get less particles. And that's really all you need to have. So for some shots, you might want to do a lot of the particles just underneath the surface and introduce new volumes, new motions, new all of additional attributes, that kind of stuff. So you need more particles, because doing that kind of stuff on the volumes is a pain. But sometimes you don't need to do any of that and you just need some cool motion. So you might as well simulate less particles, right? Increase your simulation time again and make things faster for yourself by cutting down the amount of particles you are simulating. Then if we look at the substep settings, they are existing on the solver like everywhere else, and we have the standard settings of timescale, is you want to do super fast moving fluids or slow motion fluids. We have minimum substeps and maximum substeps. These are used in condition with in addition with the CFL conditions here. So basically what that means is a CFL condition is how many voxels can a particle travel in one step before it needs a new substep in order to resolve that motion more precisely, right? So if we have a very slow moving simulation, leave all of this by default. If we would have a very fast moving simulation, you probably want to up your maximum substeps and maybe lower your CFL a little bit, giving you a more precise simulation, right? But normally I try to keep all of this by default and just make sure my simulation is stable enough without massive substeps, because that just means a massive overhead in the simulation, right? So let's set this all back to default. Cool, so now we know the basics of the flip object, where to set the resolutions, how to set some solver settings, and how to make sure that our narrowband works and that our substeps are nice. We know where all of that lives. So let's drop in a little collision in here and then export this simulation so that we can look at meshing and whitewater later on, right? So as an animation that we would drop in here, I'm just going to make a torus. Call this guy anim. When we go inside of it, I'll make it a bit smaller, and let's rotate it around the x-axis, right? So maybe 10 degrees per frame, so that we're getting this kind of animation, right? So the easiest way to make things collide or flip is to use the collision source node. The collision source node is really cool because it calculates your motion blur on your geometry, as well as creating an SDF for you. So if we take a look at that guy, we see that we're generating this volume based on the volume settings here. So we can like lower this guy and make a bit more precise volume. So the way you use this and the way you bring this into the flip solver is by merging both of these together. And then I just use a null as a hook so that I can call this within the solver. So let's just call this collision. And now whatever we change here, my solver will still pick up this null, making sure that I can switch out all my animations, plug in multiple animations, and it will work without an issue. Cool. Inside of our dot network, the way we collide with this now is by using a static object, pointing at our animation, collision, and now we turn on use deforming. One important thing is when you use the collision source, go to collisions, change this mode to volume sample. You already have an SDF generated that you could cache out to disk before you simulate when you have a very heavy collider. So make sure you use it, and the way you do that is by changing the mode to volume sample. Okay, and now all we have to do is plug this into the merge and make sure the static object is the left input and the simulation we want to collide with is the right one. Now sometimes if you use a lot of the Houdini buttons, you will get a static solver. You do not need a static solver. You can just delete this guy. All you need is a static object, right? So if I hit play on this now, we see that the collisions work, and we're getting a donut that's slowly rotating in the water, and everything is working as expected, right? Very simple, straightforward flip simulation. So the way we cache this out, let's not look at that donut, let's look at a nicer one. So the way we cache this out is by going into the flip tank fluid here, which is just a geometry sum. And in here, there is an import flip tank node. And this guy looks at our dot network, looks at our flip tank object, and then brings in a bunch of these objects that we saw contained on the flip object, right? Brings in our geometry, which is just all the particles. And then it also brings in a surface layer, which if we show this guy, this surface layer for flip simulations describes by being in positive values what is outside of water, and with negative values what is inside of the water, standard SDF, but 0 is perfectly the surface, right? So wherever the water is, we're getting a 0 right on this edge, okay? So that's the surface layer, very, very useful, very important to have. And let's go over here and set that back to invisible, and the velocity value matches the velocity. Now one more thing we want to turn on, just because we want to do whitewater with the simulation later, is on the top object we want to go to flip solver, particle motion, vorticity, and turn this on. Now this setting is so important that I actually saved a flip solver as a new version of it internally for me that simply has that turned on by default, because that's definitely something you don't want to forget. Really, the amount of times I had to resim a simulation in production when I started out because I didn't check the vorticity button is kind of embarrassing. So make sure you check that every time you do a water simulation. You never know what you're gonna use this guy for, right? Always have your vorticity turned on. Now in here, the import fluid, comes in with all our attributes, comes in with our Houdini volumes of the surface, and our 3 float values describing the velocity vectors, right? Now that gets pumped up directly into a fluid compress node. Looking at this guy, what it does is actually really cool. Let's turn this off so we see it better. What it does is it takes all our simulations, brings them in, and now has a few options here. The first one you see is the cold bandwidth. So cold bandwidth takes your surface volume and just kills all the particles that are further away from the surface level than, well, what you describe here, right? So if you want to keep all your particles, you would set this to a 10. If you want to remove as many as possible, set this to a 3. Default is 4, which is quite nice. Unless you really are low on disk space, you can like crank that down a bit more. I like having the extra particles, so leaving this at 4 or maybe even a little bit more is normally what I do. The next option is keep particle attributes. Now, Houdini comes in with a bunch of attributes like new apart, previous, has previous, right? All these stop attributes, all of that stuff. And all of these attributes actually stack up quite a lot and keep a lot of space when you don't delete them. So what keep attributes does is it removes all of them, right? And it adds a bunch of detail attributes instead. Now, why it keeps those detail attributes is because Houdini's tools use those later on. And they're very useful for that. But because they're detail attributes and not per point attributes, each one of them just has one value. So the data size is really non-existent. But if you keep 5, maybe later on when we get into some custom stuff, maybe 20 additional attributes, each one of them per particle, all of a sudden you have 22,000 additional attributes times 5. That's a relatively low resolution simulation, right? So this data set stacks up really quickly. So Houdini here by default deletes everything but the attributes in here, which means if you do custom attributes, you have to make sure to add your attributes in here if you want to keep them outside of the simulation, right? And then it has the packed particles option. Packing particles is just nice, less disk space, it's good, very high resolution simulation. You're adding a little bit to the sim time by packing them, and you're adding a little bit of CPU time in the end by unpacking them. But if you're limited with disk space, it's definitely a really nice option to do. The other thing that this fluid compress does is it takes care of our volumes. So again, if we middle mouse button click on just the import, we see that we have 4 volumes here, right? They're all standard Houdini volumes. But if we click on it after the fluid compresses, we see that we just have 2 VDBs, surface and the volume, our velocity here. And now we see that the velocity is no longer 3 float, 3 scalar volumes, but now it is a single vector volume, right? So this guy converts our volumes to VDBs and then does a vector merge on them. On top of that, it also downgrades them from a 32-bit float to a 16-bit float, which is quite a bit better, right? We don't need 32-bit float in 99.9% of the cases for our volumes, so we might as well save a lot on disk space, right? And then we have a standard file cache node here that's set up by default to run through and cache all this out. And I'm going to do this off screen before we get into this video. Alright, so in this video we covered the very basics of flip simulations. We looked into creating a flip tank, making sure we understand the resolution settings, what all of them mean, making sure we know where our boundaries are set up, sure we know what a narrow band is compared to a normal simulation, and also how we can cache effectively the simulation to disk after we introduce some collisions. I hope you all learned something, and yeah, in the next video we will be talking about meshing the simulation. Thank you. In this video we will be taking the flip simulation we set up in the first video, and we will be looking at a simple way of meshing it using the Houdini pre-made tools. So we will be covering on how to take a simulation once cached, turn it into a surface so that we can use it for rendering later on. Cool. So the easiest way of doing that is using all the tools that came with Houdini, right? So earlier we made a flip tank. This gave us these 3 nodes. Did all the simulation, we introduced a little bit of collision in there. And now if we look into the flip tank object and we take a look at this compressed cache node, which is just a file cache, and enable load from disk, we can see that we got our simulation, which is a bunch of boxes, right? Which is not quite pretty to look at, and we probably want to look at something else. Now, Houdini comes with 2 streams connected to this compressed cache node. The first one, going straight down, is just set up for preview. So if I visualize that, we instantly get our simulation, and let's hide the wireframes, and we can see that, hey, here's our sim, right? That we cached, that we simulated, and if we visualize our donut, we see that everything is working as expected, right? So what Houdini does here is it unpacks all the points and visualizes them based on the velocity, as well as grabbing the compressed fluid surface, right? And that's all defined down here on the output of this particle fluid surface node. Now, the cool part here is that it actually doesn't just take the surface and merges them with the points. Because if we look at the surface polygons, let's look at the compressed fluid surface, right? It is quite a bit higher of a mesh than if we look at the particles and compressed fluid. And that is because Houdini actually remembers, that is one of those many detail attributes that we wrote out, how many voxels worth of particles did we save out. So Houdini knows how big this area is. So what it does, it simply removes and erodes away the surface level by this distance, and then converts it into a mesh and merges it with all the particles, which gives us a pretty decent way of looking at our simulation. Because if we would just change this to particles, you know, you instantly see through it, you see like stuff like this, and it's just a bit more complicated and a little bit less visually pleasing to look at, unless you have a lot of points, at which point looking at just the particles is very nice, right? So by default, this will just show you the particles in the compressed surface, and that is a pretty good way of looking at your simulation after it's cached. Now, when it comes to meshing, all of that is happening over here, right? So this node, which is the same node as this particle fluid surface node, just comes in with a few extra things set up for us so that we get a nice mesh out of it. So let's look at each section of this node step by step. So this top section up here is really setting the resolution of your mesh and the resolution everything else is operating on, right? All of these filterings, the regions, transfers, all of that is based on these guys. So particle separation is automatically linked to your simulation, right? That thing just needs to be the same thing, same value as whatever you're simulating with, right? Now, voxel scale is a multiplier on your particle separation. So whatever this particle separation is, we're using 75% of that, which means we get a more high resolution volume from all of our particles, right? Influence scale is a very powerful thing. And that is basically saying how close can these particles be in voxels before they merge together. So if we lower this value, you can see how our nice surface up here starts breaking apart, right? One is just every particle is just a VDB from particles basically. And as we increase this, these gaps start filling out, right? And that is a very powerful way of making your fluid feel a lot less low res and make it feel a lot more high res with everything. Because these particles here, if you would have a single droplet there, it would feel blobby, it would feel strange, but with this influence scale, you capture that area and you're good, right? Droplet scale is a specific setting used when if you would turn on droplets, which is something we might be doing in later courses during the workshop. But for now, this is set to 1. We don't have droplets, so all is good, right? And then we have union with compressed fluid surface. So what that does, if I turn it off, we can see it quite clearly, right? All of these settings up here, they are simply a VDB from particles. Okay? It's just those settings plus the influence scale. That's all it is, right? Particle separation becomes voxel size multiplied by voxel scale, right? That's just what this is. And everything else up here is just a VDB from particles. But the union compressed fluid surface option here is really nice. It does the same thing as our preview does, and that is taking our surface field and just SDF merging it together with the SDF we're generating from our particles, which now builds in this entire tank, right? In a lot of cases, you want to do that just because it makes your life a lot easier to deal with things later on that we'll be talking about a bit in the region section here. And it just makes sure that you actually cover and fill your whole tank with a mesh, which is quite nice in a lot of reasons. And then under the output settings here, we can just decide, do we just want our particles? Do we want to preview? Do I want the SDF so I can do other things with it later? Or if we want to go for rendering, we probably want to choose a polysoup. They're a lot more efficient to render, right? And then we have the standard VDB convert option if we go to polygons, which is just, how much of the surface should we eat away, where 0, it's an SDF, so 0 having it as the point of building the mesh is quite nice. And adaptivity simply describes on how much resolution exists on flat areas. If we set this to 0, you can see we get as much mesh resolution as we have voxels for, but if we increase this quite a bit, we see that our mesh gets quite low res, and this is completely based on curvature, right? So you probably want a tiny bit of this, just not to hash out more geometry than absolutely needed. And right underneath that guy, we have a simple attribute transfer. These 4 values is what Houdini thinks are the most commonly used ones, and they're definitely not wrong. Those are the ones you always want to have on your mesh, and they just use an attribute transfer to put it onto them, right? So that is our basic surfacing and meshing options. Now, filtering is really, really powerful, and the reason for that is a lot of surfaces of flip look really bad without filtering. So for example, here, if we go to the first frame and I disable the shaders in the viewport so we can see it a bit, we can see that this is actually quite lumpy, right? This is not a smooth surface, but we are simulating a completely flat tank without anything going on the first frame, right? And especially as soon as we start stepping through this, we see this is becoming super lumpy for no good reason. And I'm just gonna switch this to polygons so I can hover over this without selecting some random stuff. So here you can see we're getting these weird lumps here, we're getting all of this stuff. And as soon as you shade this with a specular shader, all of this stuff is going to show up, right? All of these little hums, all of these little imperfections, they're gonna be speck hits. And they're gonna move around and it's gonna look like your mesh has acne. So what we want to do is remove all of them. And the way that is done is using filtering. So the easiest way is to just turn on the smooth and boom, right? We removed a bunch of the lumps. Easy peasy. The problem is, if we step a little bit further in here, we probably also remove a little bit of our simulation, right? It shrinks and we're removing these top peaks. We're, blurring everything because that's all a smooth is, right? It just blurs and averages things together. And we don't want to do that everywhere. So let's mask this guy in. And as soon as we check the mask box, it will use the mask combined of all of these guys down here. So in this case, let's use a vorticity range. And as soon as we do that and visualize the mask, we can now just dial in where everything happens, right? So we can just say, well, everything with a 1.3 in vorticity should get it. But as soon as we reach, 2, for example, I don't want to do any more smoothing. And go 1, so it's feathered a little bit more. And now we know everything red gets blurred. Everything in this purple, violet color does not get blurred at all and does not get smooth. Turn this off and we go back up here to our smoothing. I can set this to a 4, maybe even a 6, right? If I want to be really crazy. I get this really smooth surface here. But as soon as we're in our simulation area where stuff is happening, we're still retaining all of this detail. So there's really barely any change in our simulation besides just smoothing out these areas out here. So that's smoothing. Very useful. Always use it. Really neat little feature to have. The other option up here is dilate. And what dilate does, as soon as you check that box, it also checks the erode option, right? And that is a cute little trick with volume modeling that is best shown on something else than fluid. We take a box, hide everything else. We do a VDB from polygons on this. Connect this and let's make this, a little bit more high resolution. So what Houdini does with this dilate option is it puts down a VDB reshape, and it puts down a second one, and it links the offset values between both of them. But the second one is set to road. We look at the first one, and now we can see that we're growing the box, right? Everything just gets bigger and we're pushing it away from the value, from 0, right? So we're changing the box. Now the erode is doing the same amount, but it's going in. And so if we disable this and we look at that, we see that our box shrinks, right? So why would we do 2 of these things at the same time? Why would we make the box bigger and then smaller by the same value? That doesn't make a lot of sense. Well, what it does is it smooths out all these sharp areas of your simulation. If we disable this, we get these sharp edges. Enable it, they get blurred. They almost get like a bevel applied to them, right? If we increase this, we can make, this quite a bit smoother. And now, especially if I would lower the resolution on it, right, we're taking away all of the sharpness. Now, the reason this is done is because water isn't sharp. There are no sharp edges on water anywhere, unless it's colliding and it's squeezed into an edge, right? So our mesh, it has some sharp points, like this guy, this peak, all of that. So turning this option on averages out these areas and makes them feel and behave a lot more like water than they would normally do, right? So that's also a really good option to turn on, and you can mask that in as well, right? So we could just say, well, don't do it in our crazy simulation area. We want to keep all the detail possible there. Then mask it out or run it over everything. It's a quite neat little thing. Now, the last option here on this particle fluid surface node is region. And region it basically just describes your boundary layers, as you can see here. If you don't use a bounding box, everything just grows and gets bigger. You use a bounding box, it just limits it. These values are being picked up right from your flip solver, so your domain is being used to enforce all of this. You say you want closed boundaries, you get it closed. You want it open, you get it open. Now, which one of those you want really depends on what you're doing it for. For example, rendering water surfaces in Arnold, you would use shading to drive really how deep through the water you see and what colors you see underneath. So you would just want to hand over a single mesh surface like this. You're rendering within Mantra, you're going to render a volume inside of this, at which case you probably need the closed boundaries. So this option really just depends on what you're doing, what you're using it for, and this very much case by case. I tend to, in a production environment, always export my water like this, because if I would ever need a full box of that for volume generation or whatever, I can just do a volume extrude, plug that in, and now I get, you know, what I need from this. But caching wise, I always cache this, just in case it's being rendered in Arnold or it's being rendered in V-Ray, or you know, a camera is positioned in a way where I would see this edge. Now everything breaks, right, if I have a surface right here, right, because I get double refractions out again and all of that stuff. So I tend to play this safe and just export single surfaces like this. The other option here is flattening, which is a quite nice option. I think it has a lot of nice things in it. Some of the things I'm not a big fan of, and that is mainly what it does. It blurs, it makes everything flat, right? It just scales it to 0 to your water level, and that's it. And it does it based on a distance value from your bounding box, which is great. It's nice, and if you have a higher value, it will, well, higher than 0.5, it will just ignore it. Like for example over here, right, we have a little bit of bumpy values, and if we lower this, if we lower this, it will just force it to 0. That's the max value it allows. But yeah, as you can see here, it just clips everything away, and if we force this out, it happens, but it's a very harsh cutoff, so you can get away with it. I tend to just do it in post caching with an attribute warp myself, just to make sure the rate, you know, the fall off is smooth and it's all controlled nicely. But it is built in, you can use it, and it's really important to use it if you're going to render this attached to any other mesh, right? If you want to render this extended, you need to have this flat so that displacements and everything lines up, you don't get accidental shadowing. So it is a very important thing to do. I'm just not a big fan of the implementation here, right? And pad bounce, really useful. It basically just makes everything a bit bigger. And that's really, really nice. You can just, you know, export a bigger mesh to lighting, for example, so that if you have a shot like this, right, you now don't need to simulate all of this area. You can just go and pad the bounce, and you're good, right? Your camera is covered with mesh. Now, talking about covering things with, covering your camera with mesh and seeing everything in the camera, you can export all of this camera frustum cold. We go to cameras and we just zoom in a bit and we make a camera. It's beautiful. And we go over to the flip tank and back to the options here. We select flip by camera and cam 1. Everything disappears. Now, why does everything disappear? The way Houdini and all of these tools do camera frustum clipping is by using the volume option. So the volume node is very old school. It's not a VDB. It's a very, very old Houdini node. But it has a really cool option which is called from camera. If you select that and now select your camera and hit accept, and we give it an initial value of 1, visualize it, all of a sudden we see this nice little frustum here. And if I increase the set far, and let's give it a bit more rest so it doesn't look horrendous, all of a sudden we see a volume in the perfect shape of our camera view. And I have options for where do I want this volume to start, where do I want this volume to end, and down here I have overscan options. So let's say, we want to make sure that we have enough stuff on the side of the screen, off screen, so that it doesn't look really strange, or if there's a lot of motion blur we see past the mesh. So you want to give it a little bit of overscan, right? And you can just do that in all directions, just like that. And now you have a nice volume that you can use to capture and delete meshes with. And that's exactly what this option does, right? All of these settings now, they're here. The only thing is you don't have a resolution setting, because that's picked up directly from the resolution settings earlier. And if we look at this and we give it 15 meters, then boom, we now have a water mesh that is perfectly viewable from our camera, and we don't cache more surface than what we. Now this is great, right? This is fantastic. I urge to be careful with this, right? It really, really depends what you are doing. If you just do this in order to have a mesh that you can play around with, awesome. If you plan on rendering this, and unless you have like a crazy simulation and you definitely can't save all of the stuff that's outside of your camera, I personally would always export everything. And the reason for that is shading, right? All light rays, if you do it in Arnold or if you do it in Mantra or V-Ray, they all bounce into this mesh, change the way they behave, and then either trace and show a different value and different density in the case of Arnold, or simply become denser and denser as they go into the volume in the sense of Mantra. But all of them have this phenomena that the edges of a water surface are a lot brighter than the middle. Which means if you now cache and remove all the mesh that's just outside of the camera, you have a good chance that you will get this halo feeling around your shot, especially if it's very bright lit. To avoid this, right, in a studio environment, either give this maximum bounce so that definitely doesn't happen, or just turn it, right? Like, it is a great feature to have. It cuts down on all the IO, it cuts down on disk space, it's very optimizing. But for water and for water rendering, I personally would not feel comfortable risking this, especially what happens if the camera gets updated and you just want to tweak it a little bit, right? The simulation is approved, everything is great, and they just want to film it from a slightly different corner. All of a sudden you have to re-export your mesh, right? All of these things in a production environment, I would be careful with that unless you're being asked to frustum clip it, then do it. And if you see like, hey, maybe export one frame, make sure shading is fine. But yeah, as a default, I would keep that turned. Cool. So that concludes this video on meshing. We've taken a look at the meshing options that Houdini comes with, taking a look at the particle fluid surface, gone through all its settings, looked at what it does, looked how it operates, and yeah, we are now ready to either export this mesh or what we will be doing in the next video, which is talk about whitewater solvers. Thank you very much. So in this video, we will be taking our simulation and run some whitewater on it. For that, we will be using the standard Houdini whitewater solver and all the options Houdini comes for it. And we will be looking at all the settings, see what it does, see what it doesn't do, and just get a feel for how whitewater works within Houdini by default. So for that, we will be using the same simulation. Let's look at that again, which is our little torus or donut swimming around in the water and just splashing around a bit. So in order for us to set up whitewater on this, we will be using the shelf tools again, right? Because we're covering the basics, so yes, let's use what Houdini gives us. If we go up here and we select the whitewater option, it now also select a fluid to generate the white water, right? So we select our fluid object and hit enter, and that instantly pops us into a new dot network. So before we do anything here, let's take a step back and just take all of those new nodes and lay them out a little bit better so that we know what's going on. So Houdini put down these 3 new nodes for us. First the white water source, the white water sim, and then the white water import. Guessing white water import will just import our simulation and do some post-processing, so let's hide that one for now. And let's focus on our source to begin with, right? The source automatically is connected to our good old compressed cache, which is our water simulation, right? Houdini, because we selected it and we used all the tools, it knew that this node is called compressed cache and that it will be used for our white water emission, so it automatically brings that in. Then the next node in here, and by far the most important one, is the white water source. So if I visualize that and we go in a little bit, we see that there is nothing going on, right? It's completely empty. And if we middle mouse button click, there's one field and it's density, but it's like tiny. So it's really strange. There's something not working quite well. Now, the reason it's not working is because our underlying simulation does not meet the default prerequisites to run a white water simulation with. And what I mean by that is the values are off for the emission, right? So here on the first tab under emission, we can see that there's like limited to depth and there's a maximum half width and all of that. All of this you can just leave by default. For this at least, you can play around with that a little bit later, but for now that's just all default. The important thing to look at is speed range. So if I set this to 0 and 1, all of a sudden we see that a little bit of stuff appeared, right? Like there is some volume here, and that means that we will get some emission because the white water solver is really particles emitted from volumes. Now, every time I deal with anything that emits particles from volumes, I'm very skeptical with my visualization of this. And the reason for that is there's very low density volumes that do emit, but they show up really, really badly in the viewport. So what I normally do is I use a volume visualization node, and I plug this guy in here, and as the density field, I just give it emit, which is the field generated by the white water source, and we crank up the density. And oh Lord, what do we have here? We see there's a lot of areas that are emitting that we probably don't want to emit, right? All of this stuff there is probably not really what we're after. So let's just take the white water source and up this a little bit, speed range, so that we're left with only our particles, right? So all of this is happening and all of that is great, but still looks a bit strange and looks like we're not getting a lot of areas, right? And that is where these tabs up here come into play. The way these work, these all are settings and like individual ways of isolating particles that should be emitting white water. And all of them get added together, and then that needs to fall within the speed range. So the speed range is the master of all of these guys. So if I turn off all of those, acceleration, vorticity, and curvature emission, we get nothing, right? But at the same time, if I turn on vorticity and I make this, for example, 0 and 1, so almost everything emits, and now in my speed range, I can just isolate and remove that, right? So we have the speed range as the master. So all your emission needs to be at least at this point 0.9 fast and 0 and greater than 1. We probably want to have that a little bit more ranged. And on top of that, they need to have at least these vorticity values, right? So it's 2 prone layered. This isolates the vorticity, says emit from that. Speed range says you're good to go or you're not good to go. So let's play around with these vorticity values a little bit so that we get something that actually makes sense to emit. Right, so let's up this a little bit and let's just lower this guy a little bit so that we get some vorticity values that make actually sense to spawn some foam from. Now let's turn off vorticity so that we can dial in the acceleration without overlapping with the vorticity. Again, all three of these filters get added together and then multiplied. So if I show both of them, I now don't know if my acceleration is doing this or if my vorticity is doing these things, right? So if I turn off the vorticity, now I know this is the only thing I'm getting from my acceleration at this point. So let's lower this a little bit. And acceleration basically grabs the differentiation in speed directions, so or speed in general. So anything that just gets faster on one turn very aggressively, that will be picked up, right? So let's say acceleration wise, these are fine. Turn that off again, go to curvature, and let's just play with this value a bit and see what we get. So curvature is basically saying what is the angle of the velocity, and the higher values means lower angles and less curved angles are allowed to emit from, and the lower this angle, the crazier basically everything needs to be, the more bent the velocity field needs to be in order for it to be picked up. So let's go a little bit, in the middle, add these to it, and now we can turn back on the acceleration and then the vorticity, and now we have this volume to emit our white water from, right? So now we have our source and that's all set up. So let's take a look at the white water solver itself. We deep dive into this guy. We see there's a white water object. The white water object has a bunch of visualization things and some bounce and friction settings, but that's it. Everything else is handled on the white water solver. So unless you're setting bounce and friction, you don't really need to touch this guy ever. It's just a container for all the data generated by the white water solver, right? So if we just hit play on this by default and take a look what happens. Boom, white water, foam, bubbles, everything generated, everything done, everything good to go, right? We can also see this is slowing down quite a bit already. That's one of the things we'll be talking a lot more next week about when we talk about custom white water solvers. The speed of this thing is not fantastic in my opinion, so that's just something to keep in mind, right? But let's take a look at all the settings and everything that's going on so that we understand what the Houdini solver does, so that we can then choose to use it when we need to use it. The first thing I'm going to do is I'm going to go over here to the limits and turn those off. It's just a lot easier to navigate if there's not a massive box in front of your face. Alright, so water scale, voxel size, all of these settings. What are they? What do they do? So white water scale is the resolution of your white water. Now the white water solver uses a pop fluid inside, which is very much based on a scale. So the bigger this value is, the bigger your shapes are going to be. The smaller this value is, the smaller your shapes are going to be. Well, the smallest shapes you can achieve. The thing is, the smaller you go, the heavier it gets as well. Right? So if we set this to 0.1, for example, and hit play on this, this simulates a lot faster, but we can also see, second, once this builds some foam right here, that what the white water solver does is keep all the particles separated from each other, right? That's all it wants to achieve, is equilibrium between all these points. Now, the distance of these points is defined by your white water scale, right? So if we lower this guy to 0.5, we will see that we get, first of all, more points because the emission amount is bound to this value as well as getting everything spread out a lot smaller, right? So we're getting a lot more tight-knit areas which means we can get a lot smaller details as well, right? Because the particles don't want to be so far away from each other, which is really nice. It's really neat, but it comes at a cost, right? So the more details we want to introduce, stuff like this, right, that gets expensive, and that is completely bound to the size. If we would simulate this at 1 again and look at this area over here and just let this run through for a few frames, we will see that really we won't get that level of detail, right? Now it ripped just like before, but there's no strings connecting it in between. It's just a big hole, and that's just because the particles don't want to be so close to each other to actually form these strings, right? They want to be far enough away from each other so they form big holes or big patches, like we can see here, right? Also nice. Probably not what you want for a lot of the foam shots you're working on. You're looking for those small details, but it's good to know that this is all coming from the whitewater scale. So let's reset this, give it a decent scale amount, and look at the next settings. Now, voxel size is interesting. So voxel size is used by the solver internally to generate a new field on here, which is called foam density. So what it does, it actually checks how many particles are in each area and stores that as a volume, right? So that we can then later use that volume to determine shaping options of how much foam attraction do we want to run. If it's more dense in this area, which means a lot more particles being in that area, we probably want to run slightly different shaping and in the end rendering operations over this. So that is what this voxel scale is set, right? That field is being driven by that. And as we can see here, if we look at foam density, it's just hard coding this value. So this is not a multiplier based on this. It's just setting the value. So maybe we go a little bit more detailed for this to begin with. Just, you know, if we're using this for shading, if we're using this for driving shaping operations, we probably want to have some detail. Cool. Foam location. You can shift stuff. That's basically 0 means directly on the surface level of our simulation. You can offset that and move it higher, lower, whatever you want. Leave it at 0 for 99% of the simulations, unless you're having a very specific case, then you can play around with this. Depth range is basically saying, well, what is the minimum value? How deep can things go? That's also used later on for some forces and for some limiting factors and all of that kind of stuff. I would also say in most cases you can leave that at default. Now let's take a look at emission, right? Again, we're feeding this a volume, and what we're getting out is a bunch of particles, which means Houdini is doing a lot of stuff internally to actually emit things for us, right? So now here we have an emission amount, we have velocity offsets, velocity multipliers, maximum speeds, and lifespans, right? So the emission amount by default is kind of bound to the whitewater scale up here, which means if I go low res on this, right, so we get bigger shapes and the particles want to be within a 0.1 distance to each other and they're kind of trying to achieve this equilibrium, Houdini automatically spawns a lot less points than if I would go higher resolution here. But I have the option on the emission amount to oversample that. Now keep in mind, the solver doesn't care. The solver wants to achieve equilibrium between the point distances, which means automatically, well, we're making something that kind of looks like my fried egg this morning, right? It just blurs out and it becomes this big shape, and yeah, there's no more details in it. And that's just because we're emitting so many particles, all of which want to be a certain distance from each other, and that just pushes out to the sides, makes this whole thing a lot bigger, right? So unless you have a very good reason for it, I would just keep this up at 1. Velocity offset, you know, it's kind of like, don't change it too much, again, unless you have a specific case. Velocity multiplier, very nice, very important to have. Let's say you want to add a little bit more of a wow moment into your simulation and really crank up the whitewater and have it fly a lot faster and a lot further than your water sim. Crank up the velocity multiplier. Or if you need to achieve the opposite, where your whitewater is just going absolute mayhem, crank down that velocity multiplier. Speed limit is fantastic. It's a cute little thing. And what it does, it basically removes all spikes. So if you have velocities on a point that shoot out forever and go really, really fast, well, sometimes you want to limit those back in, right? So this just won't allow any particle to be faster than whatever you set the value to here to begin with, right? Really nice to, oh, I have this one particle that flies away and goes crazy. You can just limit its speed here. And then lifespan, standard lifespan setting, it's a pop simulation. So this will live for 5 seconds, right? And then we have some advanced options down here. So if we look at those, we can change the seed, and then we have the same settings. One second. So here we have advanced, under the advanced settings, we have aging rates. So these are kind of extenders of the lifespan. So let's say you want your bubbles to live forever because you have this very underwatery, bubbly shot. You can just tell them to live a lot longer than the foam or the spray. Very nice feature, very good to have like some individual aging control over all of these areas. And down there you have a velocity noise in case all your particles go in the same direction and it's a bit boring, like we kind of have in this case, right? You can just add a little bit of a noise to all of that from the beginning, messing this stuff up a bit. So if we add these guys, and now let's do something very little, we can see that we add this so that we just break up those shapes just a tiny, right? Nothing too crazy. And now if we hit simulate, we see that everything is working just fine. So I'm going to pause the recording here, and I'm going to run this through at a little bit higher resolution with a little bit more whitewater scale up here, a little bit more lower whitewater scale, so that we can see what this guy does. Right, I'll be back. Okay, so we are back, and we've had some of the simulation run for 100 frames. Again, this is the same settings that we had, no changes, all default, and this is what we're getting. Right, it's just a bit more high resolution. So we can see that we're getting some nice foam patterns, we're getting all of that, and we're also getting our whitewater colliding with the edges of our simulation tank. So let's take a look at where that is happening, and we want to use that, seeing that it's going quite crazy over the corner. So if we go back into our whitewater simulation at work, and just for us to play around with stuff, I decrease the resolution again. And if we go to our whitewater solver, we get to limits, right? So limits, as we established before, has the big box that we turned off in the beginning. That's a bit annoying to look at. So if we enable that again, we can see that this box is defined and set up directly from our flip solver. So it's the same settings. Also our boundary conditions, like if they're closed or not, are being taken over directly from the flip object. So if we turn all of this off, now all the particles that go outside will just be killed, which is quite nice, right? That's probably something. So now let's turn these off again and look at the other option that we have in here in limits, and that is collision swap, right? We probably want to collide with some stuff just to make sure that the whitewater interacts correctly. So let's point this at our collision, the same one that we pointed our simulation to, and here it asks for the SDF name. So the easiest way to grab that is to go to our collision source. On the volume we see the name, and right now it's called collision. Again, it's Houdini, you could call this whatever you want, just grab the right name, go back to the whitewater solver and paste that. So now we will get collisions. Now let's go down further in the settings to forces. Now forces on the whitewater solver are interesting because they are described by two things: gravity and buoyancy. So gravity is the usual, it's what we're used to and all of that. Buoyancy describes how fast particles under the water surface rise towards the water surface, right? And there you kind of need to do a little bit of the math of like, they are being pushed down by minus 9.81, but they're rising by 13.08. So really, they won't be rising 13 units per frame. They will be rising roughly 4.8, 4.73 units per frame, right? Per second, not per frame, which is okay. And then when you scroll down, we have all of these confusing curves here. Now, these curves are described based off fit ranges. So, oops, I changed the value here. So the depth range here is sampling the SDF of our surface field. And up here is positive 8, down here is negative 0.8, positive 0.8, which gives us exactly at 0.5 our surface field, right? That's the middle of our surface. So here we can see this buoyancy curve means it starts dying off when it comes closer to the surface, and then it, gets pushed up a little bit more. And for the advection of our particles, that's again for everything underneath the water. How much of the velocity field should they be using? When they're really deep, not so much, because bubbles far underneath the water get affected less by the waves. We will be talking a lot more about that during the beach break lecture later in this workshop. And the closer to the surface level they get, the more they're advected, and then obviously as soon as they're away from the surface, they're falling off again. Now you might be wondering why these ramps don't stop right at 0.5, right? They're all kind of overshooting it by quite some bit. And that is because the foam layer also needs to be advected by the water surface. And if that's not being advected by the water surface, it will make weird streaking effects and everything kind of freaks out a little bit. So the side effects guys give it a little bit of a range, a little bit of a limit, just to make sure that all the foam is also being advected. Now the spray that's flying off of the surface and like hangs in the air and goes up, that leaves this little margin so fast that it doesn't make a difference, and this just helps clean up everything. So there's no risk applied with having that a little bit over the edge, right? So that is our limit forces, which means if you want your particles to rise a lot faster, increase the buoyancy. Slower, decrease the buoyancy, right? Simple stuff. But now the main section of the solver comes, and that is the shaping and the look and how things work and how they feel, and that is under foam. So here we have a bunch of settings for clumping, for erosion, and repellent. So I will be running a bunch of flipbooks with the same simulation we saw earlier, right, with these kind of settings, and I will be running a few different versions of this, and then I'll come back and we'll be talking about the results of that. Okay, so I ran a few of those simulations, and here's our default. So this is what we're having without any shaping changes, without anything what we had before I went off to simulate some things. And the only thing I changed here from the version before is run this through with the volume limits turned off so that our foam disappears. So the first setting under the foam options that we have is our lumping, right? So how strong do those particles want to be together? And here we can see, especially on the last frame, we have a few solo particles that are just floating around out here, over there, right? That are just not very neat and give us this more broken up foam pattern look. Now, if we run this with a lot more, how is it called? A lot more constrained stiffness on the clumping, then we see that we get all of the sudden very nice patterns in some areas. Like to compare these, right? 47 over here, like this is a lot more messy. Here we're getting a lot nicer, more defined details. Look at the last frame of this. We see that there's really not as many loose particles just floating around on the edges, right? We're getting nicer, bubbly, spherical shapes. We're getting, a little bit of outbreak here, and we're getting this just to look a little bit neater and a little bit more defined. Now, too much clumping can obviously backfire and just remove a lot of the realism of the look, but I think a little bit more stiffness in the constraints will add quite a bit to your simulation. Right, so this is clumping. More clumping, cleaner, less clumping, a little bit more broken up. Right? So the next option here is erosion. So the way erosion works, it basically uses that density field that was generated at all times, right, of how many particles are active where, and uses that range density to slowly kill off particles. So if we look at what this looks with a quite heavy erosion setting, just so we see what happens, we can really see how this foam just dies off a lot quicker. And the reason is it's very low density areas here, right? It's high density, it's nice together, it's clumped, and now it becomes low density as these particles push further and further apart from each other, and now we're starting to kill those guys off. As the new foam comes in, spreads and dies off. So if you want to have like shorter lived foam that dies off in an organic manner and just not just over lifespan and everything dies off at the same time, using something like erosion might be a very nice go-to here. And the last option, that's really about sculpting. Adhesion is not about sculpting and making new shapes, is repellent. So again, this is our base simulation. And now if we look at our repellent simulation, base, why does it, sorry, this is the repellent simulation. So here we can see that the repellent adds a lot. It does make a massive difference to your simulation, right? Here we can see how the foam just spreads out now. It gets emitted, it moves with the surface, and now it just spreads out and all the strength takes over, which means in a lot of areas we're getting really blobby shapes. What we don't get anymore is these snaky behaviors, this kind of behavior of the foam being pushed together and squeezed and all of this, or like here randomly changing direction. So I personally always like to turn off repellent. It just means you need to play a lot more with your lifespan and with your shaping tools to make it work, right? So what repellent introduces is a bit of this more like stringy behavior on a big level, which can work quite nicely. It can also really backfire. But if you turn it off, that behavior disappears, and what you're left with is just all particles trying to reach equilibrium at their distance while floating around on the surface. That really covers all of the shaping tools that are there on the whitewater solver. What the last option here is adhesion. And adhesion simply tries to force the particles that are foam onto the water surface. Right, as we can see here, these particles are floating on top of the surface level of these particles, right? So they're not going below every now and then and above, and they're not bouncing around. Adhesion simply says, hey, if you're within this range of depth, make sure you stick to the surface, right? Make sure that you're really trying to be as close as possible to that, which is nice. You know, it just cleans up the simulation, removes that popping, and removes the chance of your whitewater being underneath the surface every now and then and then coming up above it. But that is whitewater simulations. That's what it does, and that's all really you need from those. So now let's take a quick look after the crash. I'll be right back with the scene opened up again. Alright, so we are back. And we have our flip simulation here that comes in from a DOP network. We're using a DOP.io. That's all set up by Houdini already, this whole chain here. So the DOP.io simply brings in our geometry. Now the set density uses the density grid that was before with a bunch of values and everything to basically remap a density attribute onto the particles that we're simulating. The reason we are doing that is because whitewater in Mantra is completely rendered as volumes. So the way Houdini does that is by simply rasterizing those particles and using the density attribute to really drive the density of the smoke around, right? So if we have a denser area of particles, right here, for example, there's a lot of particles, right, compared to here. Our smoke will be a lot more dense over here than it is in the middle here, right? Now, the reason we're working with density and not so much like p-scale and making them smaller and all of that is just cohesiveness. All of these points try to achieve a certain distance to each other. So if we start playing around with p-scale and varying that based on how dense it is and all of that, it will just break apart and all of these single dots will become dots instead of one big nice area that works as a sheet of foam, right? Now, this can go directly to rendering and you render it and it looks good. But in order for us to get speculars on this within Mantra, Mantra needs something called a gradient field. So here within Houdini, it automatically just puts those down for you when you use the whitewater options. And that is a VDB combine, which just grabs the density field on 0 in case you combine this with something else, and then a gradient. And that gives you now the gradient of everything facing, like where do things face from our density field, which can be used in the shader to drive specularity. And those two combined, our density and the gradient, is what we're exporting for shading and what we're going to render. So in this video, we've covered the whitewater solver, how to dial in emissions, and how to make simulations that work, and you know, how we can control them, how can we get different looks of them, and yeah, covering the basics of the whitewater solver. In the next video, we will be going over more of the settings of Flip rather than the basic tool sets. We've just covered how to do a basic simulation, how to do basic meshing, and how to do basic whitewater. Now that we have this trifactor of parts that go into a whitewater simulation, really, we're going to spend more time this week looking at the Flip solver itself, and we're going to talk about the different volume shaping options like viscosity, density, air entrapment, divergency, surface tension, and so on, and getting a deeper understanding of what all of these do so that we can then next week do some cool stuff. Thank you. Okay, so now that we've established a good base understanding of the Flip solver, meshing, and whitewater, the three main components of a water simulation, let's take a deeper look at the simulation settings on top of the Flip solver. So in this video, we will be looking at the viscosity settings, at standard viscosity, as well as variable viscosity. So to start with, let's take a look at what a standard viscosity video simulation could do. Here we can see like a little star emitting a very high viscosity fluid into an ice cone, just building a little bit of a soft ice and then collapsing on itself and slowly filling out the gap within the ice cone and just sinking and settling in over time. With a very high viscosity, as we can see, it maintains these shapes and it maintains all those ridges, whereas normal water would just splash all over the place, right? So let's take a look at how we can do something. So I'm going to go a little bit faster now than we've gone in the last 3 videos, just because we've established this base understanding, right? So first we need a flip object, as well as a flip solver, our two main components of a water simulation, right? Then we make gravity and plug that in. We go to the initial data, remove all the initial data, go to guides, particles, visualization, change this to particles just because we don't really want to see those sprites, right? Now we, by default, if we do everything by hand, like I just did, let's change this to dark, we end up with a pretty big bounding box under the volume limits. It's 50 by 50 by 50. We don't really care, that's fine, but what I want to do right now is drop some high viscosity stuff onto the ground, and doing a ground collider is unnecessarily expensive, so instead I'm just going to move this box up so that it lines up perfectly with 0 at the grid. It's just y divided by 2, and now we can go onto our flip object and close the boundaries, which will now give us some collision on them, right? So this is our sim network. Now we also need some sourcing of a high viscosity object that can be falling to the ground. So let's take a pig head. And let's just go in here, make this a little bit bigger, and look from the side. We see that it's quite a bit under the ground. Let's just lift this up a little. So now what we can do is just make a null and call this source out and call this source. And we can go into our simulation network, initial data, surface sub, and point our source at our pig, which now instantly fills this with particles based on the resolution of everything. I'm also under limits going to turn off that box, just so I can use space G to really zoom into my simulation. So if this is on, I zoom into the whole thing, and then I have to zoom in and all that. Oh, turning off the visualization helps a lot. So now if we look at the simulation, we see our pig head just falling down and splashing and behaving like standard water would, right? So let's reset this and take a look at viscosity. So if we go over here to viscosity and enable this, we see that there's a bunch of options down here, right? Solve viscosity with additivity, viscosity from attribute, stick on collision, all of that kind of stuff. And a lot of it is grayed out, probably because we need viscosity from attribute and stuff like that for it. But first of all, we just want to give this one full viscosity, right? All the same value. So the way we do that is on the flip object. On the physical options, you see viscosity here. That just gives the whole container, all the water, the same viscosity value. So we're going to give this 100 to begin with, and let's hit sim on that. And now we can see that everything is still falling apart and it's still squashing, but it's doing so a lot less, right? The water is no longer rushing to the sides and like floating away. It is just kind of trying to stay together. And as soon as we increase this value to a lot more, we see that it more and more holds its shape, and now it just kind of looks like a very sad candy that was way too long in the sun. And if we increase this even more, now we're getting no compression on this anymore, and we're just kind of maintaining the shape of our little pig. Now, as you can already tell, viscosity needs immense values to really hold very strongly to an object. The thing is, viscosity is also very slow to solve. As you can see, a lot of this time down here goes against gas viscosity solvers, right? So having viscosity turned on slows down your solver dramatically, but it solves it, right? And if we decrease the resolution on this a little bit, you know, we can see that good old pig is actually landing and holding its position. Now for high viscosity things to look at, I actually like to change my visualization of it. Go to guides, visualizations, and turn off particles, turn on surface. Now this is obviously a low resolution representation, but it's a lot easier to really see if like the ears are collapsing or if this little pig is like just being squashed. Like if we remove a bunch of those zeros again, we can see that the pig is just kind of thing, right? And it's just a bit easier to look at this and see, oh, are there still shapes left in there or not? It's just a bit more convenient to do it this way. So this is setting viscosity and the basics of viscosity, right? It just makes things stick, and it makes the fluid stick to itself, tries to stay in the same position to each other as it was on the frame before. The higher the viscosity, the more it will try to stick to those values. Now, luckily, Houdini can do viscosity because it's useful for a lot of simulations, but even better for us, it can do viscosity on a per particle basis. Because right now, again, we're setting all of the particles to the same viscosity. So let's say, for example, we have a pig head here, but we also have a squab, right? And good old Squab wants to be a viscous creature as well. And if we look at both of these and make this guy a bit bigger, and let's move him over to the side, a little bit higher so he doesn't penetrate the ground. Sorry about that. Let's look at him a bit more like this. Rotate him a bit so he doesn't penetrate. So if we have both of these guys, and we would go here to simulate them, reset sim, response incorrectly. Let's look at, I'm pointing at picket as source. Important to use those hooks. And now we're getting both of our creatures, right? They're now behaving exactly the same. And that might be what you want, and then you're lucky and you get away with slightly cheaper calculations. But let's say we actually want the Squab to melt a little bit, right? Just a little bit in some of the areas. And that is quite hard to do if all you have is one linear setting, right? So luckily we can set this back to 0. Luckily Houdini added this option, viscosity by attribute, which now means it just on all your particles grabs the viscosity attribute and feeds the solver this attribute. Which means if we now go to initial data and remove this, and we set up our sourcing a little bit more custom, and by a little bit I mean we're going to do a points from volume. Here we go. Plug this guy in, give this a bit of jitter scale. Let's just grab the resolution so that these guys match up. So now we have the rest of this, and let's not actually do this per object, but as a total, but let's do this per object. So now we can just create a new attribute here on the pig, call it Viscocity, and give it an immense value again, right? So it's just crazy. And because we only want to emit on one frame, we can go to our sim network, initial data, particle field, and source. And now here we go. So now our pig head does not come in with any of the viscosity. There's two explanations for this. First off, and the most likely, I misspelled it, which happens all the time with me. Second option, play this, is that I misspelled it, which is very good. And now we can see that we actually have variable viscosity, right? So actually everything works now. Our Squab melts, our pig head stays solid, stays united, right? Which is exactly what we wanted. We wanted individual control over certain things. But because it's an attribute, can we just source all of these viscosity attributes on the first frame, or are we able to really manipulate them throughout the simulation? The really cool thing here is we can manipulate the living hell out of it. So let's say we actually want to make a nice little gradient based on the density of all of this, which we just do with the VDB from poly on this guy. And then we run an attribute swap over our points and just do a volume sample on this. And that will now just grab our surface field, and with a fit range, we can just throw this onto color real quick. So here, we now know that it's an SDF, which means it's negative in the inside, positive on the outside. So let's just set it the other way around, which if we look at the light, gives us this nice little gradient. Now, you can see that actually our output max is 0.3. That's an SDF thing. It has to do with how many interior bounding voxels you have. If we just hit fill interior, you're good to go there. So now this gives us really what are the particles on the edges and what are the particles deep inside. And if we do the same thing, for our good old squab, we will see that his tentacles and like his claws and everything is, you know, a lot darker than the inside. And if we just store this attribute, and let's make both of them super strong, and let's just store this attribute as color on both of these. And maybe we don't store it as color, we just store it on here as mask, so that we have this attribute on our squabs to really use in the simulation and manipulate viscosity over time. So now if we go back to our simulation, we increase the resolution here a little bit and play, we see that both of these guys are quite solid now with the viscosity, right? We gave them both very high values. Squab looks kind of cool, the way it's collapsing here. But let's say we want to slowly start melting these guys. The way we can do this is with a simple geometry warp plugged into the particle motion. Let's go in here, bind, bring in the mask, and then we can just fit range our mask, which we know is a 0 to 1 field, right? It's a value on that, and we just say, you know, the outside is 0.9. And now all we have to do is grab bind export, and because I know I will spell it wrong, I'll go outside, grab viscosity, paste it here, and then we duplicate these, and now we can apply this whole thing, right? So this is a very simple loop of knowing that a geometry warp evaluates over each point on every single frame, which means I now can read in an attribute, manipulate the attribute, and then write it out again, which means before the solve I get, for example, a value of 1000. In the solve I multiply it by 0.9, which now means the result out here is 900. That gets written to viscosity. The solver uses 900 as the new viscosity, and on the next frame I start out with 900, multiply that by 0.9, output that, and so on, right? So I have a recursive loop automatically, because we're in a simulation, that now slowly scales down our viscosity on the edges. And if we look at this, now we will see that stuff like the tentacles are a lot more floppy, his ears melt, right? It's becoming sad. He's slowly melting in the sun. But everything inside is still staying quite strong with the viscosity, so we're keeping that core, right? And this is an easy way of melting objects using very simple recursive operations and using variable viscosity. It's very powerful, very easy to set up, very easy to control, and you can do quite nice things with it. For example, here I just did a snowball, a wax ball of very high dense viscosity, and then I have a heater here in the middle that runs through, that slowly cuts through that ball and melts it. And at the same time, these little bars here on their side are slowly but surely heating up, and all this wax too. So they're melting and like getting squashed to the sides here, and so you get this nice little like tearing feeling, so that the ball drops. Right? Doing things like this is really simple, knowing that viscosity is just an attribute, and you can change it, you can manipulate it, and you can make some quite fun simulations with it, right? So that is viscosity with Houdini Flip. Thank you. In this video, we will continue our deeper dive into the flip solver and all of its parameters. This time, we will be looking at a nice little feature which is called Divergence. Divergence is extremely powerful in the right cases. Basically, it pushes or pulls particles away from each other or towards each other in sometimes very little, sometimes very extreme ways. And the best way to visualize that and look at it is really to start setting up the simulation. So for this case, we don't want to do anything with pig heads for once. We want to burst a little bubble. So we're going to make a sphere, make this guy a bit bigger, and just scatter a lot of points onto the sphere. Notice how I'm not really creating like a shell or inside volumes or anything. We're just giving this one thin layer of particles, just like an eggshell basically. And we call this our source. And source here, paste that here, go into our network, make a flip object, and this time we don't need any gravity. It's because we want things to float around it. Here under initial data, we change this to particle field and then point it at our source. Again, here you can really now see how important that visualization change is. Particles, this is now way better to work with than before. Believe me, I'm trying to move the mouse at the same speed, and Houdini just kind of lags unless you have a 3090. You probably don't want to deal with that. And we're gonna go to volume limits and turn those off again. Okay, so now we have a beautiful sphere that just kind of sits here and does nothing, right? Which is great, and we probably want to give this a slight more resolution. Nice, good. So the way Divergence works is it operates on a field level. So all these particles, everything that we give them gets added to a field later, and that field either pushes all the velocity away from itself or attracts all the velocity to it, right? This is also the only option on the whole flip solver where we have to go to the flip object in order to enable it. With viscosity before, we could have just given it an attribute and it would have been fine, but here we need to go to initial data, scroll all the way down, and add the divergence field. Otherwise, nothing that we will be doing after this will work, okay? So we will be making a little bursting of a bubble. And the way we do this is by just making a little sphere, and let's place this on the edge of our bubble. And we call this burst, right? So if we go into our simulation network now here, we can do a geometry warp, plug that in, and sample as our input. It's the first input, grab the sub, burst, and we grab the sphere here. We go inside, and now we use a point cloud open in order for us to manipulate and drive the divergence field. Right, so we're just going to sample our sphere position in a 10, and let's do 5 meter radius, and we're just going to check if we find a point there. And if the point, if this happens, that happens to me sometimes where we're getting this weird manipulator, there is a hotkey to get rid of it. I normally am a bit impatient and just make a new work over, and we're back. So here, if I find a point, so if I go greater than 0, which means I have found this point, and all the points within 5 meters of it should find this point, I now have a 0 to 1 value. So if we just plug this into color, so we can visualize this. Boom, there we go. So now we have our effective radius of this burst. So all we're going to do here is make a switch. Set this to manual real quick, and make 2 constants, and then a find export. So we're writing a new attribute. And because we're not reading this attribute in first and manipulating it, we're just adding and overriding it with new values, either inside of our lookup radius or outside. We just set this per frame, every frame, right? So if we go back to our dot network and to our flip solver, we can go to volume motion and divergence. And here, now we enable divergence by attribute, and just copy this guy. Go in, and now paste it into our bind export, which means we're now writing divergence as a data set. And if we hit play on this, nothing happens. And the reason why nothing happens is because we're feeding it 0 and 0. Now the important part, and divergence is quite different there from like viscosity. For example, minus viscosity doesn't mean that things melt faster. It's just how much viscosity do you have or do you have none. Divergence works in the opposite way, right? So if we say everything within the radius has a 5 positive divergence, we will instantly see, let's hide everything else, that all of these particles are starting to move, and they're moving away from the divergence field in the best way they can, right? So this now pushes all of our particles away. And here we see a prime example of a nice little option on the flip solver, which I waited for to get to until now, which is called receding. It's godsend and devil send at the same time, because we have this little eggshell, right? But here it's making this big poof of particles, right? Which is very, very strange. And the reason for that is receding. So receding, under the particle options, receding samples all the points within each voxel, and it has a goal of amount of voxels, that amount of points that should exist per voxel, which is 8. On the surface, there should be 50%, 150% of 8. There should be 12, right? And now it also, and that gets triggered if oversampling at boundaries is turned on. And now it has a birth threshold and a death threshold. And those are quite interesting, because a birth threshold means as soon as there's 4 particles or less within one voxel, it's going to add new particles. And as soon as there's more than 12 particles per voxels, it's going to kill them, so you're left with 8. Which means this simulation continuously spawns new particles and removes them, right? Now, if we have a very thin sheet like we have here, and we do some crazy effects on it, what we get is a lot of water being generated, because they're single particles, they're alone in a voxel, so receding kicks in. So what do we want to do? Turn it off, in this case, right? And if we hit play now, this is going to run a little bit faster as well, because we're not counting voxels continuously, we're not adding particles continuously, and we can really see and appreciate how all those particles want to get away from the divergence field. So all of these guys, they're just pushing away from each other, and they're just trying to spread out as much as possible. Now, the thing is, we're looking up in a perfect circle, right? Which means we're not masking this out based on where the particles are to begin with. We're just saying everything around the sphere in a 5 meter radius should be pushed away, which means out here we also have divergence. And that might be that you want that, but in our case, let's refine this a little bit and just make sure that it all stays within a decent distance to the shell. The way we're going to do that is just making a new input on our geometry block, grabbing our source, pasting that here, and now we do a point cloud open again. Let's copy this guy, second input, and we grab a PC filter. So a PC filter will just filter whatever attribute you want from the 10 points, from the 10 first points that were found within a certain radius around the position you're sampling, right? I hope everybody is familiar with point cloud opens. We will be using them a lot. I love those things. They're really, really good. But if you're not aware of them and how they work, let me know afterwards, and we will do a quick deep dive on point clouds. But for now, we're just going to grab the position, which is the averaged out position of the first 10 points we find, right? And we're going to grab a distance. So we're just checking how far away is everything to our current point, right? And then we're just going to do a compare, and we're going to say if this distance is less than 0.2, 20 centimeters, then add the divergence. So now we're doing a multiplication here, which means we find the point within 5 meters, but only if we're within 20 centimeters of the original shell are we adding any divergence. And if we hit play on this now, we will see that the particles burst apart and they're flowing away from us. And after a while, they just kind of continue drifting as they are, and they don't keep like pushing apart. They don't keep going crazier and crazier and crazier, which is quite nice. And if we go and visualize our divergency field, flip object, guides, visualization, all the way down at the bottom, divergence, it wants to visualize it as a grid. Not a fan of that. We can just go to the visualizer and say use smoke. Now we can see, especially if we turn off the particles, that we have a very thin shell of divergence here, right? So positive divergence pushes everything away from itself. So what does negative divergence do? -5. Negative divergence attracts things to themselves. So now all of these particles, they want to be one. They want to come together, which gives this really nice cell-looking breakup of our little flip shell. And if we're just going to do this everywhere, we will see that it creates these really interesting shapes and these really interesting patterns of you know, fluid attracting itself and creating really interesting effects, which I have used in production before to burst alien bubbles or to break force fields apart and stuff like that. It makes for really nice, interesting simulations that look and behave extremely organic. For example, if we go -50 here, quite extreme, we're now all of a sudden really ripping this whole area together quite heavily over very few frames, right? And if we do the opposite of 50, we will kind of like get this imploding effect of everything kind of just breaking apart and like getting pushed away as a ripple washes along our sphere, which is really kind of nice as these particles just start pulling each other away. But it's a very interesting look. And this could be even more interesting, right? Because we're just setting that divergency on every single frame. We can go even more extreme and say, well, we want to introduce the positive divergency within the shell and when it's like in this area around the sphere. But what happens if we're greater than our distance lookup? And let's add a little bit more to it. Maybe we want to switch from whatever we're adding divergency wise here and instead go to a negative divergence, right? So this now should do the burst of everything pushing away, give us this nice shockwave, but as soon as the particles are 40 centimeters away from the shell, they should start attracting themselves quite extreme, right? So we're getting the burst, everything goes out, and now they start attracting themselves very extreme. So what we're getting is this kind of feeling of like a burst that's running outwards that then instantly kind of starts eating itself apart into these smaller particles, right? And this is a very extreme example, but this way you can get a nice popping of a fluid happen, right? Which is really neat. And you can do crazy interesting effects these ways. Well, just playing a little bit but with the divergence, maybe introducing some extra forces, introducing some extra fields in there. But divergence alone can do so many pretty things for you. It's really powerful, and you should try and use it in some of your cases. Yeah. So this is divergence. We looked at what it does, how to visualize it, how to seed it and manipulate it, and yeah, it creates just really fun little effects for you, and can be very useful when used sparingly and here and there in splash simulations to break them up a little bit, uprest them a little bit, we will be talking a little bit more about divergence in that manner in the later workshop tutorials. Thank you. In this video, we're going to talk about the air option on the flip solver. So this time, to start with, we're going to look at quite a few experiments I ran just to show you guys what high resolution slow air simulations do, and what some of the massive issues with the air option are, and what some of the nice details are that you can get from it. Alright, so let's take a look at this playblast. What we can see here is at the top, standard flip, right? Nothing changed, nothing turned on. It is all without receding, so receding is turned off. But besides that, it is just flip, high resolution, colliding with these objects, right? In the middle, we have the air option turned on. No changes, just turned it on. So now we can see what the air option should be doing and what it is doing in a lot of the cases. And that is simulating entrapped air in an object. So up here we have the particles, and down here we have a void. It's just an empty collision object. So what the air option tries to do is simulate how this air gets pushed up through the fluid, because all of this water down here is displacing the air and forcing it out, right? Forcing it to take up this other space up here. And because of that, it's bubbling and we're getting this like aggressive motion happening. And then, in this case, something strange happens and the whole container fills up with fluid. Very odd. And then over here, we're seeing another case where we're getting very nice initial motion, right? We're having nice bubbles coming up. It's a much smaller hole, so a lot less air and a lot less water is coming through. And it's working, it's bubbling, we're getting this underwater motion. But the bottom is filling up and the top is not really dropping in water level. As a matter of fact, it's actually rising in water level as well, right? So seeing this, I thought, okay, so it might just be a precision issue. It might just be a problem that it's not high res enough for the kind of collisions I'm running. So I took the same simulations and ran them again with a grid scale of 1. As we know, that is way more precise than the defaults. Ran them through, and what we ended up with is this, which is a much better result than the middle, I must say, because mainly we're not generating a lot more water. And these actually feel relatively okay, but it is very clear in comparison to our standard simulations that the amount of water is now a lot less that we're ending up with, right? So that is quite a drastic problem that comes with the air option on the flip solver. Now that we know this, we're going to go through and see how that is set up and what some of the conditions are that we need to enable on the solver. But I thought we start this out by looking at some of the major issues that this option has on the flip solver, so that you are aware of what to look out for, and also what some of the limitations are and where you should and should not use it if you come up with a task that would require you small little bubbles rising up in a container. So let's start out by going to Houdini. This is the scene where I simulated all of these things in. But let's just make a new scene. Start from scratch. Cool. So we'll make a container for our water to fall through, and we're just gonna make a 5 meter tall box, and let's do a 4 meter wide, and this poly. Yeah, that's all right. And we'll just subdivide this a few times down the middle. And now we select, front view, then select points. Here, we're just going to scale these guys into the middle, making a bit of an indent here, right? And now with a simple subdivision, we can subdivide this guy to be a bit leaner. And we get this little stamp in the lower the subdivisions. These axes get a bit spherical shape a bit more. That should be better. So now, point numbers, of course, we can now just grab these guys again and scale them in, which now gives us this as a result. Right, so we can squeeze these, looking at the cage, it's completely broken, but looking at the actual surface, we're just fine. And on top of that, I would like the top bit to be a bit smaller. So we're just gonna crack this in like this, and then we're gonna grab both of these guys, shrink them, but we end up with something like this, right? So now first we make a collision out of this. So we just do a collision source, this, and plug this guy in, merge the two in outputs, and name this null C for collision. Then I want to fill the top part with water. The easiest way to do that is to use a clip. And the clip gives you a very nice clean cut, even if there's no polygons there, right? So it actually splits all your polys up, and we can just raise this guy up a little bit, and do something here. And now with a polycap, we can fill this hole, and now we have our emission object that we can use. So if we go out, we call this emission. All right, let's call this object setup, because it contains our collision as well as our emitter. Let's just visualize. So let's make a dot network for our actual simulation. Off and water inside, typical flip object, flip solver. Right? Always need those two guys, always need a gravity. This time to mix it up, we're gonna turn off the visualization first, and we go to initial data, and we're gonna feed it our function as a setup, and we're gonna a little bit of scattering, so it's a bit broken up. And that's it really. Now we need to bring in our collision. Static object pointed at our collision. Collision, change this to be volume sampled and merge it with our simulation. Like that though. Okay, so let's hit play, and ooh, well that's a really strange, weird behavior that we're seeing here. So what is happening here? If we turn off the display here, we can see that all of the water instantly gets pushed out to the sides of our collider, and it's just kind of like sliding along the edges. And the reason for that is that Houdini collides with SDFs, right? So inside of the SDF, inside of our little cool little shape here, it is negative, and outside it's positive, which means Houdini tries to keep all the particles and all the fluid on the positive side of the SDF. In order for us to change that, the easiest option is on the collider itself, go to the collision objects and just hit invert sign, which now just flips all the minuses to positives and all the positives to negatives. And if we hit play here, we see that the water is stuck up there. Now the reason it is stuck up there is resolution, right? We have a very thin neck of a fluid here, and it's needs quite a few voxels resolution to actually fall through this guy. So if we turn this off again, and we just go up here and give it a bit more of a res, right, all of a sudden our fluid is starting to fall through the hole, and this is just standard flip doing its thing, right? So let's reset this and maybe make this hole bigger, just so we can iterate these simulations just a tiny bit faster. Grab these and make this more like that. The nice part with rigging up the sources and the collisions like this obviously is that we can just change this one slider and everything will work from there. So now our water is falling down and filling up the hole. We're just gonna let this run through, and I'll be right back when this is cached. Okay, so let's take a look at how the simulation looks with no airfield entrapment, no nothing, everything just default. And we have a flip simulation that fills a container and splashes around a bit, and everything is a-okay. So let's actually play blast this real quick, just so we have it as a comparison, right? So we're gonna go play blast, remove this, make a new one, and just hit play blast on this. Should open it, run through in like half a second, and I'll. Okay, so here we are. We just ran the simulation through, same settings as before, everything default, and we end up with this nice little simulation that's filling this class. Now, to me, this is a lot less water than this, but let's go with it for now. In general, I would probably turn off receding on this, just to make sure we're not introducing a lot more particles into the simulation. And let's actually, just for the fun of it, run the simulation through with and without receding, so we can just make sure that receding is not an issue that's throwing our airfield simulation out of the whack. And I'm just going to make a camera for this, so that we have an equal comparison every time. That's a pretty decent way of troubleshooting something. Just checking different versions. I'll be right back. Okay, so I took our simulation and I ran it through a few times just to look at what we get from it. And this is the results with turning receding off. Now by default, Houdini always comes in with receding turned on, because a lot of the open ocean toolsets and all of that use receding very, very heavily, and it can add some nice things to your simulation. But as we saw in the Divergence, in the Divergence class, it does create a little bit more particles when you don't always want that. So this is the result with just turning on the collisions and hitting play. This is what we get from it. The water slowly falls in, drains the top tank, and makes a suspiciously large amount of water in a much bigger area at the bottom, right? It's quite a lot of water. And as soon as we turn off receding, we get the same water behavior, water falling down, everything is good, but we're getting, I would say, a way more reasonable amount of water at the bottom of our glass, right? So keep this in mind every time you do a simulation and something water levels feel off or particles disappear or get created. Receding is it's a mixed bag, and sometimes it will work for you and sometimes it just won't. And that's an issue. I personally err on the side of turning receding off unless I know I absolutely need it. So yeah, for most of the scenes we will be doing, I will have receding off from now on, right? So if we go back to our scene, receding is turned off. All we have to do in order to get airfield entrapment is to increase the resolution a little bit, just so we get this a little bit faster. And then we go over to volume motion, air, and turn this on. So now if we hit play on this, we see that, you know, there are some bubbles coming up and some bubbles bursting through. We see that the stream is being diverged, that we get a nice curl up here, that we get this little popping, and, you know, we just get stream pushing through and air wanting to go through this hole, right? And we get it to slow down, to speed up, all of this based on how much pressure is being exerted to push all that liquid out again. And we can see that the liquid's flowing into the glass at much lower rates than it did before, right? Here it just rushed out, gushed down right away. And now with airfield turned on, with this air turned on, we see that it makes these glocking, like gluk, gluk, gluk kind of sounds, right, in our imagination. And we see that it really tries to limit how much water can run out of the top and how fast it can fall down, simply because there is a lot of pressure and there is a lot of space being taken up by air, and it's incompressible. So in this case, the simulations worked out great for us, right? Air worked right away, everything is good. Now, side effects themselves, they give a few things that should be taken into consideration. And one of them is that if you ever simulate this with a massive container, and on your container under volume limits, default of dynamically resizing the field is turned on, there could be issues with the air option. So dynamically resizing, what that does is it takes this massively inefficient container and it makes it way more efficient for us. If we look at our guides and we look at our collisions, we will see that we only generate a collision field. I'm gonna turn these guys off again, just so I can zoom in. We're only generating our collision field within a small radius around all of our points. So our collision field actually never gets as big as the massive box that we have, right? Which makes us really efficient. Now the problem is with airfield entrapments is it is reliant on the pressure and the air being enclosed, right? So the air not being able to go anywhere, which means right now for Houdini, this area is open. There is air can go in and out of this collision, which means we might not entrap the right amount of air here. So what we should be doing is take this guy and make it much, much smaller. And we're going to visualize our geometry and then just make sure we fully fit around it, which it seems we do perfectly. And turn this off again, and now go here and turn off the dynamically resizing, which now instantly on one frame builds our box, and we're just going to make this a bit bigger so that there's no holes in it. So now this created our collision field inside, right? So now right on the first frame we establish where the air can go and where the air can't go, just to help stabilize simulations a little bit. Also, we can't do this really with narrowband as well. Yeah, that's really the main limitations of it. You can't run narrowband on it, and you need to kind of turn off dynamic resizing. You can get lucky and it will do something. It just won't be as accurate as if it will be if you turn that off. I'm gonna sim this so we can look at a playplot of it. And here we have a simulation run through at a higher resolution with the air option turned on, and we see that it's getting like some pretty interesting nice behaviors of the water, like logging down and then speeding up again and slowly draining from the top as there's a lot of bubbling action happening. Also, what I find always very interesting is how the fluid actually gets pushed to the sides and runs around the fluid container a lot more than it does normally. Like here it kind of does it and then it just kind of collapses, but with the actual airfield turned on, it does it in a lot nicer fashion, which I always find very interesting. And then also we just have this really nice feeling of like almost a water bottle popped over, which will run, and every now and then we'll get air entrapped into it, right, and have these drawbacks of clocks happening. That covers the air option. There's not much more to it really, besides it does a very specific behavior, and now you know how to use it and also what to look out for with receding and some of the issues that happen through the air option. That leaves us with only surface tension to cover in the last video. Should be a pretty quick one. Thank you. In this video we will be going over the surface tension settings on the flip solver. It's a pretty straightforward process, so we're just going to make a box and then a dot. So surface tension is really cool. It does what water should be do, which is averaging out sharp corners of a water simulation and simulating this tension and the traction of a well of water in and of itself, right? So if we go here and we just set up the initial state here and we give it a box, and now let's give this some jittering, and let's start this out without gravity turned on. We go and turn off volume limits so we can zoom in a bit better, and we give this a lot more resolution. So surface tension lives, like all the other ones we talked about, under the volume motion tab, surface tension. And if we enable this, we keep this off by default and just have a look at this, we see it's a cube, right? Very sharp edges, no gravity applied to it, none of that. And as soon as we turn on our surface tension, we see how all the corners of this cube that find very strong high curvature start attracting themselves towards the middle, right? So we're taking these corners and we're pushing them inwards, which then naturally means we're pushing the flat areas outwards. And this gives us this really nice wobbling motion until the fluid finally reaches a spherical shape, right? So this behaves, in this case, very much like water does in space. And it gives this very realistic feeling to water. It gives these small droplets a lot of the little wobbling. And yeah, it just gives it this really nice feeling, watery feeling. So that's surface tension. And you can give it a lot more surface tension, which will now make it react and introduce a lot more of its force. Now, a very interesting thing with surface tension in general is as well that if we go and make a ground for this, so we go 24 meters, so we get the collider here and we close the boundaries. If I turn off surface tension now, we just let this box drop as soon as I turn on gravity. It just falls down and collides, right? And it just slides away, and we get this normal feeling of not really any internal strength existing between the particles, right? They just slide away forever. And let's actually make this not go forever, but for 10 minutes. If I go and turn on surface tension at a default of 10, what happens is that this fluid still slides away, but you can see how some areas here are creating actually these streams, these like pockets of water, which is a lot more realistic than if I turn this off and we just get this blanket of water, right? It just feels like there's no strength in it, nothing is really happening. And yeah, so surface tension just takes the volume, finds on the surface field, finds the high pinch areas, the high curvature areas, and then it uses those to kind of blur everything together and pull the fluid together. And with very high surface tension, you can see how all of these strings, they just all want to average out into spheres. So they're just sliding around and trying to find each other, and when they come close, they attract, and you know, they come closer here and they slide around, and they're doing actually really kind of neat behavior, which is nice. So surface tension does really cool things, does really nice things. It's a very simple setting. You should probably just turn it off. It just makes simulations look a bit better. Now, if you have simulations where you're pushing really the particle motion quite extreme, you get this pretty big torn splash, you might want to turn it off. But in general, you get more interesting shapes with it turned on. All of these blur settings down here, I quite frankly never use. It's we go through those and we turn off the gravity again. So we just put you here. So we have our good old box. So this is normal surface tension. As soon as I turn on enable surface blur here, it does a lot less of that, right? So it does a little bit strange motion, collapsing the insides, right? Just trying to blur these things out. Average, which takes these sharp corners away and isolates them, while the flatter areas are still trying to attract themselves, which just gives this really strange expansionist feeling. So this to me just doesn't really have a place in standard water simulations. It does look interesting, right? It does make this really nice noisy shape. I just think in general that's not the kind of behavior you're looking for if you use surface tension, right? So I turn this off, and then we're just simulating surface tension like this. We're getting the averaging out, smoothing out those corners, smoothing out the spikes in curvature in our surface field, and we're getting a quite nice liquidy behavior. The nice part of all of this is, right, if we make this container quite a bit tighter, so we this 2 by 2, so it's quite close, drop our gravity back in. So now when this splashes, we're getting like droplets, right, that really form, and let's just make it even smaller. So it drops and it splashes, and we're getting like, when the fluid separates, right, it separates into nice little droplets, and it separates into like attraction, and they do very nice little fluidy behavior things, right, having these droplets split up as they come up and have them attract to each other, break apart. That's just very nice liquidy behavior, and all you have to do is turn on surface tension. So if we turn surface tension off here, we see that all of a sudden, right, we're getting these massive spikes, and then we're getting this mass of particles. Everything's falling down. Surface tension back on to default. And we're getting those big spikes, but now we're getting nice and stringy behavior. Right, all of a sudden, these particles in between, they're attracted to the fluid, giving a much more realistic look. Right, and as everything collapses down, right, we're getting these individual droplets form, and we just get a realistic look. Right, and this fluid just looks a lot more realistic than if we simulate it like this. Right, this just becomes really messy, and it just doesn't feel really like a liquid. Now, as you can see, some of the splashes have a lot less energy because they're being averaged out, right? Because of those high spike areas. For example, here was one nice one. It comes down and it splashes sideways like this. That's quite nice, but all of this area would be dampened because the fluid wants to hold on to each other, right? So forces to break out, generate those droplets, generate those splashes, need to be a lot higher to actually happen. So that's one thing, one downside, I guess, in some cases that you could keep in mind for surface tension. But in general, turn it on. It should add nice features to your simulation. Welcome to the assignments. Congratulations for making it through the first week of the Advanced Water Workshop, covering some of the basics. And with the first week of assignments, I would like you guys to reinforce some of those basics as well. So what we're going to look at is doing a little high viscosity, variable viscosity simulation. All right, so if we look at something like that, we can see in this little example file, we have a few collision objects, we have a ground collision object, and then we have variable viscosity going on in our flip simulation. Red, very low viscosity, and black, very high viscosity, right? So we can really see the difference in flow speed, where this little red here is pushing the yellow down faster, and here we can see how this like ring of dark, very high viscosity fluid is really holding everything back, right? And that's nice, and over a lot of frames that's just flowing and mixing and running down. But we pretty much covered exactly how to do something like this, right? We looked at high viscosity sourcing and variable viscosity sourcing. So this shouldn't be an issue for anybody in this workshop to do, and it should be pretty straightforward. So what I would like you guys to do is actually not simply doing something like this. I would like you guys to do a little bit more advanced stuff. So what I would like you guys to do is high variable viscosity fluids, but I would like you guys to make your colliders objects of influence, right? We looked at how to source all of this in the viscosity tutorial, but we've looked at masking areas of effect a little bit within the high divergency video, right? And how divergency works. So now the same idea of masking in different behavior is applied here, right? So we can really see how the lava flows over these top two rocks up here, and how slowly over time everything around this rock is getting much lower viscosity, right? Almost like this rock is heating up all the fluid on top of it, right? So it runs faster and we get this nice stream. On the other hand, this rock here slowly but surely starts slowing down our viscosity, well, increasing our viscosity and thereby slowing down our fluid, right? So this is just a simple example of how objects with the correct masking and accessing of attributes can really drive and change your simulation outcomes, and how you can say like, ooh, I need some faster flowing fluid just here after this rock in order to address client feedback. Something like this would very much work for that, right? So I want you guys to explore a little bit how to mask in effects, how to manipulate the viscosity data, and how to change that on a per frame basis based on objects and however you choose to mask that effect in. In general, stay a bit creative with it, have fun. It's a pretty straightforward, simple assignment. And the important thing is that you enjoy it and that you really just use the tools that are there, and that you take everything you learned from this first week and try to apply it and try to make something interesting and cool. Here it's a simple flat box with some displaced spheres. If somebody comes up with some really cool stuff to showcase his ideas and his methods of masking and how that works, I'm very happy to see that. Alright, thank you very much, and hope you have fun with this assignment, that you enjoyed the first week. Thank you.